Hello, this is Professor David Clough again with you with our MATLAB Bootcamps, and this is the first screencast for Bootcamp number 2. You can see here that we're going to focus on using MATLAB to solve typical problem scenarios that we encounter as chemical engineers. And down below you'll see an outline of what we're going to discuss. The three major sections are algebraic models, ordinary differential equation models, and then a third section which includes both optimization and curve fitting or regression analysis. And in this particular screencast, we're going to be looking at the algebraic models, and then there will be 2 additional screencasts for this second boot camp. So let's move on into this. Talk a little bit about process modeling first. We develop a phenomenological process model based on mathematics describing the phenomena that we are studying. In order to solve this model, we have to collect basic data for the model, and we have to specify operating conditions, those things that might change for different sets of operations. And then we apply numerical methods. This is where MATLAB comes in order to make a prediction of process performance. Now, in some of what we do, this is where we stop, but there can be an additional step where we are able to collect operating data. And of course, this is not necessarily a full-scale operating process. It could be a pilot plant, it could be a laboratory experiment, but we collect operating data and then we compare the operating data to the performance of the process, and this yields another step which is often in the area of curve fitting or regression, where we adjust the parameters of the process model so that our comparison is closer. So that is a general picture of process modeling, and we comment that within the dashed rectangle early on, if we're designing a process or trying to solve a more theoretical problem, we will not have the operating data, etc. So developing the process model, on the left, we bring together many of the concepts that we learn as chemical engineers, the conservation balances, material and energy, and thermodynamics, mass transfer. We deal with separations, reactors, and reaction kinetics. And if we are studying dynamic behavior, we often deal with monitoring and control. The kind of equipment that we deal with are vessels, heat exchangers, piping and fittings, pumps, compressors, columns, reactors, and occasionally we get into solids handling, like having to do with crystallization or filtration. And finally, especially if we're studying monitoring and control, we describe instrumentation associated with that. The numerical characteristics that we look at for algebraic equations are whether we're dealing with a nonlinear equation and whether it's one or a set of nonlinear equations. For linear equation sets, we have a separate category based on the numerical methods used. For differential equations, we have ordinary differential equations and partial differential equations. In the MATLAB Bootcamps, we do not study the solution of partial differential equations, although MATLAB does have a separate toolkit that addresses that. And then we look at optimization and curve fitting. A possible approach when we have combined algebraic equations and differential equations is to solve them as a combined system, which is called a differential algebraic system, or a DAE. The kind of examples that we're going to consider here, you can see fairly long list. I'm going to try and use fairly realistic examples for all of the techniques that we illustrate, and I'm not going to just read through this slide, but you can take a moment here to pan down the different categories we'll be looking at and the kind of examples that we will be using. Okay? So we're going to start simple, and we're going to take a look at solving a single algebraic equation using a very simple method, that of bisection. And what we have illustrated here is a curve of our equation f of x versus an x unknown, and noting where it intersects the line 0, which means that we're solving for the value of x that yields f of x equal to 0. So that's the general picture we have. And then the bisection method requires that you start with two estimates to the solution that are either side of the solution. And the distinction here is clear to see graphically, but if you're thinking mathematically, the f of x value here is positive, and here it's negative. And if we have a normal monotonic function, then somewhere in between there will be a crossover of 0. So what we do is a simple process where we take the midpoint between our initial estimates, and we use that as the next estimate for the solution. And then we note in this case that its f of x value is positive, so for the next iteration, moving over here, it becomes the left side of the bracket in two estimates, x1 and x2, and we continue with another midpoint. And this one, you can tell, is f of x is negative, so for the next iteration, we're going to take the midpoint between these two, and it's going to start getting fairly close to the solution. So what we're going to do now is we are going to take a look at a bisection method function in MATLAB that accomplishes this. And so I'm going to pop over to the editor. And I'm going to open a script file called bisect. And it looks like this. It has some comments shown in green, starting with the %sign. But what the function's name is bisect, and the associated file is bisect.m. And it has three arguments. The first one, called fun, that is a pointer to the function that evaluates x. So that's a function name. And then the x1 and x2, just as in our drawings, are the initial estimates. And so what we're going to do with this is we're going to start by evaluating the two initial estimates. And if their product is greater than 0, that means that, unless we have a very unusual function, that the root does not lie between x1 and x2. So if that's the case, we return a result which is a string. saying that the initial estimates do not bracket the solution. Other than that, if that's not the case, we go through a loop for 20 iterations, and you might ask, why do we choose 20 iterations? Well, every time we make an iteration, we cut the interval of uncertainty where the solution lies by a factor of 2. So if we do 20 of those, it cuts the original interval by a factor of 2 to the 20, which is slightly more than a million, all right? It's the definition of a megabyte. And so we will have 1/1,000,000th of the original interval, and we're taking that as being close enough to our solution. And it's guaranteed. The bisect method might be considered to be somewhat slow, but it is stable and the solution is guaranteed. So as we come into here, very much like our illustration with our graphs, we take a midpoint as being the midpoint between x1 and x2. And then here we evaluate the function for the midpoint and x1 and test whether it's greater than 0. If it is greater than 0, then that midpoint becomes the new x1 for the next iteration, as what happened over here with our second iteration. Otherwise, the x2 value, the midpoint becomes the x2 value for the next iteration. And then after running this 20 times, we take the last midpoint and assign it to the result from the function up here called root, and we're done. Okay? So what we're going to do now is we're going to show you how we put this into action. So we're going to start by defining a function that we're going to try for an equation that we're going to try and solve, and that function is in the file fn. So here it is, and it is f of x is equal to the sine of x plus 2 times the hyperbolic cosine of x plus 2. So that is our f of x, and it is called fn. And then what we are going to do is have a script that uses the bisect function with our function for f of x to solve for the root. So the name of this is bisect test. You can open that up, and it's fairly simple. What it does is it clears things out. It sets initial estimates of 1 and 3, and then it calls the bisect function. And the one thing that you'll notice here is the use of the @ sign, all right, and with fn, and that is MATLAB's way to denote that this particular argument is not a variable, but it is the name of a function, which is what our bisect algorithm or bisect routine expects. So we have that, and then we're displaying the solution, the final solution, in the command window. So if we run this and pop back over to our command window, if we can find it here, there is the solution to the equation, all right, and to 1 part in a million. So that's how bisection works. And you know, the nice thing about it is that it's stable, it works, does require 2 initial estimates. And if you take a look at it here, about 13 lines of code. So it's simple, and that's advantageous. Now, one thing that we can do is we can come back over to our test routine and say, let's look for a solution between 2 and 3, okay? So let's look for a solution between 2 and 3, and let's pop back over, and it says that our initial estimates do not bracket the solution. So that it takes care of that. And let us come back over to the slides and review up to this point. So this is our bisect function that we went over with you and commented on, all right? And then these were the illustrations of finding a root for the solution between 0 and 3. And in this case, we tried between 3 and 4 on the illustration on the slide, and it showed that that failed. Okay? Now, sometimes as we're going through these things, we look for ways to enhance our functions that we develop to solve equations, for instance. So one thing that you will note, let's come back over to our editor, is that we by default chose 20 iterations because we're more or less assuming that one part in a million is going to be good enough for any of our applications. And so that is something that we chose. Another way of looking at that is by adding to the function itself the maximum number of arguments that we would like to, the maximum number of iterations that we would like to run. So let's open up another function that is a little more complicated in MATLAB and allows us to do that. And that is called the bisect1 function. Here it is. So this is a way of doing this which is particular to MATLAB. And what we have added here to our list of arguments is a specifically named argument var-argin, which stands for variable arguments in. And it allows our function to accept arguments, but also the function will still execute if these additional arguments are left out. So with doing this, the first thing that we do is we check the length of this var-argin array, and it happens to be a cell array. We check its length, and if its length is equal to 0, that means that the user did not specify the number of iterations, so we set that to 20. So we're here if there's no extra argument. If there is an extra argument, we take that to be the number of iterations, and we convert that by the first element of var-argin to max it. We use a cell to mat conversion because the var-argin is a cell array which can store many different types of information. In this case, we expect it to store a number, so we convert it to max it. And then we go through our regular execution here, all right, just like we had in the previous example. Okay, so let us bring up a test for that. That's called bisect1 test, I believe. Here it is. Okay, and here what we have done is we have added the additional argument of 25, all right, so that it will run 25 iterations instead of the default of 20. So when we run this, we should get the same solution that we got before, and we do that. All right? We do. That is just a detail. And another thing I will mention at this point is that sometimes the reason that we include extra arguments is to allow those arguments, let me get back. allow those arguments to go through to the evaluation of this case of fun, all right? So that's another reason to do that. But in general, what we're talking about here is to show you how you can include optional arguments in a function, okay? So let us pop back into our slides and take a look at that. This shows you how we've set that up. And so we have optional arguments, and we're computing the number of these arguments using the length of that cell array. And then we used a function called cell2mat to convert the first element to a numerical type variable, max it. Okay, good. So now what I want to do is I want to move on and take a look at a little more realistic example, not a theoretical mathematical equation. So we're going to, this actually shows the setup of that. Sorry, I didn't mention that. And it comments on the algorithm. No, this is something that I wanted to cover. I'm sorry. So what we're doing here is we're looking at the use of a built-in function to solve for roots of an equation called fzero. And this is a much more sophisticated algorithm and method than just simple bisection. And down here it describes, it uses a combination of bisection, the secant method, which is related to Newton's method, and another method called inverse quadratic interpolation. And it switches between these methods to preserve stability and yet increase efficiency of convergence. So for example, if it can use the secant method, it can converge much more quickly to the solution than if it just uses bisection. But the secant method is known for being unstable. So if it tries the secant method and is getting in trouble, it will automatically switch over to the bisection method. And so this shows an example of using that with a simple equation of sine of x times x minus 1. We want to know where that's equal to 0. And we set it up with an initial estimate of 0.5, and we just call fzero with a function handle for the function f of x here, and which is denoted up here, and with an initial estimate, and it returns the solution, and there's the solution. And particular routines, if I come down here, there's one called fzero example, which shows the code for that. And then f of m, f dot m, sorry. That's the equation that we're solving. So if we come back and run that particular routine and look at our command window, shows the solution to the equation. And that's what we illustrated. Now after this, we're going to move on to an example. Sorry, I got a bit ahead of myself there. So we're looking here at a very common gas phase high temperature reaction called the water-gas shift, with carbon monoxide and water reacting back and forth with hydrogen and carbon dioxide. And this is a reaction that can go either way. There's a forward path and a reverse path, and we can consider what is the equilibrium that might be established by the reaction, either sides of the reaction. The equilibrium is known to depend on temperature, and so we've shown the relationship here between the of hydrogen, carbon dioxide, water, carbon monoxide being equal to an equilibrium constant, which if we are at isothermal conditions, will be given by temperature, and this is a relationship for that equilibrium constant, which can be obtained from the literature. So we set up an example of a reactor operating at 1200 Celsius, all right? And here, note that here, the temperature here is in kelvins, 1200 Celsius at nominal pressure of 1 atmosphere. And then we set up an equation that needs to be solved. So we feed these amounts to the reactor, and then in order to establish equilibrium, the amounts in the reactor shift. So the hydrogen increases by X, the carbon dioxide increases by X, the water decreases by X, and the monoxide decreases by X. This gives us our conditions in the reactor for a given equilibrium constant, and we need to find X. And once we know X, then we can use it using these expressions to describe our product rates. Okay, so that's what this looks like. So we're going to take a look at this back in the editor, and let me get rid of some of these files so they're not in our way. And then I'm going to open a file called FWG. So this particular file provides a function f of x, which calculates that equation that we described here. And you'll notice that we've used the dots with the operators here, just in case we want to evaluate this for an array of different x values. So we've got a temperature of 1200 Celsius. We convert that to kelvins. We compute the equilibrium constant, specify our feed. All right. And so what I can do here then is I can come over to the command window, and I can try something like FWG. Let's see if this works or not. And that gives me a minus value. That's an x value of 150. And then I can try an FWG of 175. And this gives me an x value, a function value that's positive. So that would indicate that we have a solution for x somewhere in between the two, all right? So another way that we can look at that, if we come back over to our editor, is to open a file called water gas case study down at the bottom here. And what this does is it takes, and this is where the use of those dot operators comes in, it takes temperatures, x shifts from 150 to 175, and since we didn't put an interval in the middle, it's going to just use an interval of 1, so we'll end up with 25 or 26, I guess, different x values, and then it's going to plot our function versus those x values, just to get an idea of what our function looks like. So let's give that a try. And there is the plot of our FWG of x versus x, starting at 150 and going to 175. And here you can see that the crossover at 0, right, is close to 170. And if I actually hover the mouse on it, it will give me values for x, but you know that the next x is going to be 171. So it's going to be somewhere right in there. So that gives us a picture of it. And then what we're going to do is, now that we've looked at the function, is we're going to improve our presentation of it a little bit by opening a file called fx of m. And here, what's different is that we have included, instead of specifying them within the function, we've included the feed amounts in the arguments to the function, all right? And this is something we often want to do. We want to include operating conditions in our function evaluation, but you may recall that the tools that we use to solve the equation only have the name of the function and the unknown. So here we've included 5 additional arguments, and we have to see how do we handle that when we call a routine such as the fzero routine, and try to deal with our extra arguments. So let's come back to our slides to describe that. So this includes some comments, but it's essentially what we did to just evaluate values. And then this was the solution that we showed, all right? Noting approximately where it's located. And often you want to use charts like this to make sure that if you're using a solving routine, that you can specify appropriate initial estimates, whether a single estimate or a pair of estimates. And here is the expanded function that we described that includes the extra 5 arguments, gives us more flexibility. And then we're going to show you what is the strategy that we use to solve this. Sorry about that. So what we're going to do, starting in the upper left here, we're going to illustrate the use of an anonymous function, all right? And that's a terminology from MATLAB. We're going to have a main script where we set the temperature and feed rates and our initial estimate of the solution. And then we're going to call fzero with a function name, all right, with our initial estimates in order to find the root. The problem we have, as shown with this ellipse, is somehow we need to get these additional arguments through to our f of x, which needs them, all right? And the way that we do that, and you'll see this come up several times, is that we define what is called an anonymous function in a particular way. And that is, we have at, which is the handle function of x, but then we include f of x with x and the additional arguments. Then when we call fzero, we call it in the name of f_anon and not fx, okay? And in this particular case, we illustrate how you can call fzero instead of just an initial guess, but with an interval. It will handle either one, okay? So that's what we're doing here. So let us take a look at a couple of code examples with this. Let's start with water gas case study with plot. Okay, and first let's see how we've done this, all right? And here what we're doing is we're taking a look at using our bisect1 function, all right, which we used before. So let's bring that back up. Bisect1, and it allows variable arguments, all right? So we're taking a look at that, and then we're looking at doing this with in a loop. Now, our loop in this case, what it is set up for is we've got our standard feed rates, but then we let temperature go from 500 to 1500 in steps of 25 degrees. And so that's going to be, 41 or so different temperatures. And we compute the length of that and set up a loop to solve for our x shift for each one of those, all right? And instead of calling bisect 1 with f of x, we call it with f anon. After we get the solution, we take our solution and apply it to our feeds in order to get our product rates, and we save all of these in an array so that after we're done, we can make a chart. So when we're done, we're making a plot with 4 different curves with our product rates with different colors versus temperature. Now let's see if we can make this thing work, all right? Okay. So this shows as we go from 500 to 1500, for instance, it shows carbon monoxide and water increasing, hydrogen and CO2 decreasing, all right? So that's what that shows. And then we can come back and we can show an alternate way to do this, not using our own bisect function, but instead, there's another file down here that uses fzero. And here it's set up very much the same way, but the call is to the anonymous function using fzero and providing an interval for our solutions of x. And the comment here is since we're solving this 40-some times and the x values change considerably over that temperature range, we have to include an initial interval which will encompass all of the possible solutions. But the only real change here is right on this line here, where we use fzero with an interval of estimates to start with, instead of using our bisect 1 function. And again, having this, if we run this particular program, and I included a little tighter grid on this, it shows the same solutions that we achieved before, all right? Now, I just make a note that the way I displayed that was by adding a grid minor statement after the grid statement to get a little more detail in the grid, okay? So let's come back and cover that here. This is the slide where we just used the fzero, and I didn't include the code for when we used bisect 1. So there's the fzero in the same setup that we saw before, and you need to get used to this idea of defining an anonymous function in order to pass more arguments through an intermediate function. You'll see that various times. And this was a solution that we received, all right? And now we move on. So what we've got here is now we're going to consider many algebraic equations, and we're going to consider 2 categories. The first is linear sets, the second is nonlinear sets. Linear sets, I'm sure you've been familiar with this before, but we have a general expression here of n equations in n unknowns, and then we summarize that with a coefficient matrix, a vector of unknowns, and a vector of constants on the right-hand side of the equal sign. And then we can do that very compactly by just denoting it with matrix vector notation as A times X equals B. And so ways that we can solve equations like this, just using matrix algebra, if we pre-multiply both sides of this equation by the inverse of the A matrix, assuming it exists, then we get the identity matrix times our unknowns is equal to A inverse times V. And the identity matrix is very much like multiplying by 1. So we can represent the solution X equals A inverse times B. And MATLAB will allow us to compute the inverse of a matrix and do matrix multiplication. So that's one way to find the solution. Okay? But there are more efficient ways to do that with MATLAB, and we want to illustrate those to you now. So we'll do that with a general simple set of equations, and then we'll move on and illustrate it with an example. All right? So let us come back over. Went by the editor, sorry. Let's come back to our editor and pop back out of these examples. Start with a blank editing script here. So what I'm going to do is I'm going to define a coefficient matrix equal to 2 and minus 1 in the first row, minus 1, 3, and 2 in the second row. Notice I'm using semicolons to separate the rows, and 1 and minus 1 and minus 1 in the third row. So we're going to define that as our A matrix. For our B constant vector, we're going to set that up as 10, 5, and minus 1. And this needs to be a column vector, so we use the apostrophe to transpose it. So there we have that. And so let me just save this algebra test. And then I can, with MATLAB, I have different ways of doing this. I can say X is equal to the inverse of A using the INV function times B, all right? And if I run that, it shows my solutions down here, minus 2, 5, and 6. Okay? Another way that I can do that, which will involve different numerical methods, is do what's called a left divide with MATLAB, which is the backslash instead of the forward slash. And if I run that, there's the solution, all right? So I can do it that way. There's another way that I can handle this, all right? And that is that I can say lin solve A comma B, all right? And let's try that. Again. So there are different ways of going about this, and we review those on a slide for you here showing the example that we used. There's also an ML divide function that you can use. And these functions that like left divide and linsolve, use more versatile solvers than and more efficient numerical solvers than when you use the inverse of A times B, which is a much more numeric intensive way of solving the problem. Now that will make little difference if you have a problem of reasonable size, but it will make a difference when you have a problem with many equations, such as hundreds or even thousands of equations. Okay, so let's move on and take a look at a fairly simple engineering example here with an absorber column where we have a gas stream flowing upward through the column and we have a liquid stream flowing downward. We are assuming here that we have equilibrium established on trays or theoretical trays, 6 of them, as we go down or up through this column, and that we have an equilibrium relationship. Here we're describing it simply as a linear relationship between x and y on any of these trays. yi equals axi plus b. The operating conditions that we have to specify are the x0 and L and the y7 and G, and we want to compute the compositions on all the trays and the exit compositions, all right? So as we do this, we have a component balance that we write for each one of the trays, which essentially shows like the LIXI and GYI plus 1, all right? It shows what's coming onto the tray and what's leaving the tray, and then they have to balance. And then to make this a little easier to handle, we can incorporate our equilibrium relationship and eliminate the y variables and come up with a single linear equation for each of the trays. And as we do that, we then end up with a set of equations, a slightly different equation for tray 1, all right, and then a different equation for tray 5, all right, 6 down here. So we have 1 through 6, all right, and these are the equations that we have, and the only right side constants we have are for the x0 and y7, all right, because that is where we have our knowns coming in. Now we can then come up with some basic data. In this case, we've taken it very simply and said that the equilibrium is just A is equal to 0.7 and B is equal to 0. And then we have operating conditions where we provide some flow rates in terms of moles per second and an inlet gas mole fraction and an inlet liquid mole fraction, all right? So this is what we have, and that what we want to do is we want to set up the solution of this set of equations in order to determine the profiles for the column. So let's go back over to our editor and open a file called absorber. This shows you how we set up the problem with some comments. We do our equilibrium factor here, 0.7, and then we have our operating conditions. We have our number of stages as 6, and then what we do is we use 3 for loops in order to compose the elements of the A matrix. Now, if we pop back over, what you will notice here is that our coefficients here, all right, our unknowns only involve the adjacent unknown values. x3 is dependent on x4 and x2. What that means is that our A matrix will be very diagonal in character. It will have a main diagonal and two off diagonals, and the rest of the elements in the A matrix will be zero. So this is the diagonal element, I sub I equal 1 to n, and it involves that coefficient. And then we've got the I plus 1, which is the one above the diagonal, and that has the GA. And then we have the I from 2 to n, which is the one below the diagonal, which is L. Then we have a constant vector. In this case, because we do not have a B function, the constant vector just has a B6 equal to minus G times Yn. And then we solve the system of equations and display the solutions, okay? So if we do that, all right, run that, back over, there are the solutions for our x's, all right? And we've solved the equations. Now, of course, what we could have done is, since we understand the relationship between y and x via the equilibrium factor, we could also tabulate the y values, and we could also make a plot of those values. And I've just not taken the time to do that here. So let's pop back over to our slides. This is the setup of our equations. And you'll notice the technique we used here in order to specify the diagonals of the A matrix. This is very typical when you're looking at staged operations like absorption and distillation, because you have an A matrix which has zeros away from the diagonal band, right? Okay, so let's move on to the last part of this segment or screencast of the Bootcamp 2 and look at nonlinear equations, which is a more difficult situation to deal with. But in this particular case, looked at generally, we have a set of n equations in n unknowns, algebraic, at least some of which are nonlinear, and we can represent that in vector form as a set of f set of functions in a vector of x's equal to a zero vector of your right-hand side. Now, the f's could also include constants, and everything in this case has been shifted to the left-hand side. And a common solution technique for doing this is Newton's method, but Newton's method for multiple equations. And so what we do is we start with an initial estimate for our solutions, and then we iterate by Newton's method. You may be familiar with Newton's method for a single equation where we use a derivative function, but here we have n unknowns, so we actually have n squared different derivatives. So the way that this works is we take our current estimate for the solution and produce a new estimate with this adjustment. And the adjustment includes multiplying by our equations evaluated at the current estimate, but also multiplying by the inverse of the Jacobian matrix for that set of estimates with a minus sign. And we do that, and we repeat this until we converge. Now, the Jacobian matrix is a set of derivatives of each equation by all of our unknowns. Now, all of the unknowns may not appear in each equation, in which case some of these partial derivatives may be zero. but it is a big matrix which in some cases can be described analytically if we're able to take partial derivatives of these functions. Sometimes that's too complicated or not possible, so we use a numerical approximation to the derivative in the Jacobian matrix that we get by perturbing one of the unknowns. Here I've shown it with plus and minus delta divided by 2 delta. And that gives us a way to estimate the items in the Jacobian matrix. Okay? So we're going to illustrate that first with an example, all right? And I'll just show that on the slide. And in this particular case, I'll go over and I'll do it using the editor. Okay. So what I'm going to do here is I'm going to create a function by function error, and it's equal to MYEQNS, all right, of x, all right? And then I'm going to have two equations, FRERR1. The first error is going to be equal to x1 squared. Second one is going to be x2 squared minus 4. That's going to be the first one, x1 squared plus x2 squared minus 4. And the second one is going to be FERR2, and that's going to be equal to x1 times x2 minus 1, all right? So those represent my equations, so let's solve that. Save that as MyEQNS.m, all right? And then we're going to come in and we're going to look at what is the Jacobian of those equations, all right? So I'm going to do function EQNS x, and it's going to be J equals, all right? And J, and then what I'm going to have is J, in this case, the 1, 1 part of J, all right? If we go back and look at my equations, it's just going to be 2x1, whoops, sorry, 2 times x1 2 is going to be 2 then J 2, 1, second equation, x1 partial is going to be just x2. Second equation in terms of x2 is just going to be x1. So that computes my Jacobian, all right? That's how I can get my Jacobian. All right, and then, so let us save this. My equation's J, and then let's start a new script, all right? And we'll start this saying I'm going to have an x0 is equal to, and I'll put in initial guesses here, or estimates of 0.6 and 0.4. So those are my initial estimates, all right? And then what I would like to do is set up a for loop, and I'll just say for I equals 1 to n, however many iterations I want, and I can start by saying I'd like n equal to 10, all right? And then the basic method that I'm looking for in here is that I'm going to say that x1, all right, is equal to 0 minus the inverse of my Jacobian matrix, and that was my EQNSJ of x0, all right, that's the inverse, times the functions, which are my EQNS of x0. So that is my x1, all right? Now, the question is, here is, when do we decide to stop this, all right? And a way of considering that is to say, well, how much does x1 change from x0? So I can say something like E is equal to x1 minus x0. That's how much they changed. And then I can say, well, that represents two errors. So what? How do I decide which of those governs whether we're converged or not? Well, one way of doing that is by calling something like ERR equal to E transpose times E. What that does, it sums the squares of the two errors. And then I can say if, that will be positive, if ERR is less than some tolerance, all right? If that's the case, break. Otherwise, if not, then x0 takes on the value of x1, yeah, I need an end here. Oh. And then having that done, I can do something like display x, or if I prefer, I can say display I and x and tell us how many iterations we ran, okay? So, and then in order to complete this, I need to specify what is the tolerance. So I could say that that's something like 1.e minus 7 as the tolerance. So let me save this, and I'll call it solve my EQNS. Okay. Now the only issue that we got here is what would happen if this is, since it's based on Newton method, if it goes unstable, but we can just try it and see if we've got any dirty laundry here. Ooh, it found a mistake. So let's see what it says. doesn't like that because it wants my equations to be column vector, I believe. So let's save this, come back and try again. So it didn't like that display. Like that display of I and X. So let's just display X and display I. So let's come back over and see what we've got now. So what it get rid of that previous stuff. I want to display our last solution before we get out, so that will be the X1. There we go. Going to put in a couple of semicolons here so we don't see anything along the way. There we have it, all right? So it showed 6 iterations, all right? And it showed the results that we're getting from this in terms of X1. I think that illustrates what we want to show here. So let's just make sure X0, let's put our apostrophe here. Start this with a clear and a CLC, which would be typical. There, okay. So it shows the that it took 6 iterations. It didn't require the maximum of 10, and those are the solutions for X1 and X2 of those 2 equations, okay? So that, the other thing that I'd like to point out as a sort of a well-known trick is that if it turns out that your solution is unstable and it blows up, a trick sometimes that is used is to add what's called a deceleration factor here between 0 and 1, for instance 0.2, and what that does is it doesn't allow it to converge as rapidly, but it keeps it stable, all right? So that's a typical trick. So let's run that and see if it makes any difference. Yeah, you see here, it didn't get to the solution before it hit 10 iterations. So it was taking longer to get there. So if I include my maximum iterations and take it out to, let's say, 20 maybe, and let's see what happens with that. It still is converging at 20. Whereas if I set my deceleration factor to 1, which means no deceleration at all, and run that, that should take us back to converging within 6 iterations. Okay, that's maybe more detail than you wanted to see, but I wanted to illustrate at least once the steps that we go through instead of just pulling up files that are already developed, the steps that we go through in putting together a solution based on a particular algorithm. In this case, it was method. And another way to do this is using a built-in function in MATLAB. So let's illustrate that here. This same set of equations as we had before, but in this case we're using a built-in routine in MATLAB which is called fsolve, and you can solve it with supplying the Jacobian, or you can ask it to solve the equations without supplying the Jacobian matrix, and it will use approximations for the Jacobian matrix. So what we've shown here is my equations, which I had from before, and then we're shown using fsolve with our initial estimates, my equations, and it comes out with the solution that we got with our own code. But it didn't need the Jacobian. And then over here, we're showing where we actually have a function which returns the equation errors and the Jacobian matrix. And then we can have fsolve solve it, that including the Jacobian matrix, and it knows then to use it, and it will come up with the same solutions. Okay? So let's move on to the last example that we're going to handle here, and it is one which is a calculation of equilibrium for a steam boiler or steam water equilibrium. And here we're modeling the gas phase or the steam vapor phase. And we're using two equations to do that. One is the ideal gas law, which is shown here on the left, with the things added in terms of the mass of the vapor and molecular weight of water, and also the temperature in Celsius and converting it to kelvins for the ideal gas law. And then for the equilibrium, we're using the Antoine equation for the vapor pressure, which has three constant parameters and the temperature in degrees Celsius. And so adopting a particular set of units here of pascals for pressure, cubic meters, kilograms, molecular weight for water, the appropriate units and value for the gas law constant up here, temperature in degrees Celsius, and the Antoine equations for that set of units, the Antoine parameters. Having those basic data, then we can set some operating conditions of having a mass here in kilograms and a vapor volume in cubic meters, and then we want to solve these two equations for P and T. All right, so that's the background on the example. And so what we do is we set up each of our equations set equal to 0. Those are they. And then it turns out that with a little bit of work, we can actually write down what is the Jacobian matrix for this set of equations. That's not always possible, but here we can do it. And then it raises a problem that you run into, a practical problem. And that is that given our units we chose, the typical values for our PV term up here can be 10 to the 6th, whereas terms in the second equation here are closer to unity. So that means we have a scaling problem between the two equations, and that can cause numerical problems in solving them. So a practical way to do that is to scale the first equation so its terms are similar magnitude to the second equation. And here what we do is we divide the first equation by 100,000. That doesn't change the solution, it just scales the magnitude of the terms. And then we have to come in and we have to modify the Jacobian mounts also by the 100,000. So what we're going to do is we're going to show you how we can set this up for solving it using the fsolve routine in MATLAB. Let's get back to our editor here. And we'll open a file which is called solve steam equal. Right? And then this wants to use a function called steam eq. So we'll want to open that up. So looking at this function first, it is going to return both the equation errors and the Jacobian, and it's going to have the unknowns plus m and v. And m and v are the two operating conditions. So we need those two to solve it. Then what it does is it sets up the basic parameters here. We could have passed through those parameters, but we're doing it here. And then it unpacks the x unknown vector into p and t, which are familiar variable names. And often you do this just because it makes your equations easier to understand and debug. And then we calculate the equation errors for our two equations, and you'll notice this is scaled down by 10 to the fifth. And then we calculate the four items of the Jacobian matrix, and the FERR and J are then returned. So if we come back to our main script, let's see how we go about doing this. We set up our operating conditions, M and V, and then we put in initial estimates for pressure and temperature, 200,000 pascals and 110 degrees Celsius. And then we define an anonymous function. Here it comes again, where it's a function of x, which is what our solver wants to find, but it's based on steam eq, which has the extra variables m and v. Now in this case, we've done a little bit of extra work with the fsolve routine, where we've set some options associated with it. One is specify objective gradient. That means that we are including the Jacobian. And the other is display none. And what that means is otherwise fsolve gives us a bunch of intermediate results, and we don't want that, we just want the answers. So that could be left out. And then what we do is we call fsolve with our anonymous function, our initial estimates up here, and our options variable, all right? And then we use a little more care using the fprintf statement to display our results, okay? So if we run this, there are the results that we get. And you'll notice that they're somewhat different than our initial estimates. Initial estimate was 200,000 pascals and 110 Celsius. So those are the solutions. And again, the kind of features here that you want to be aware of are the idea of passing the variables through M and V, all right, that fsolve doesn't need to deal with, but it needs to pass them through to our steam eq function. And we set them up here. And then to including some options for the fsolve, routine. And again, if you ever need more information on that, back on your command window, if we just type fsolve up here in the top, it's going to take us to MATLAB help, and it's going to provide us with a lot of information and examples on how to use fsolve. All right, so there we go. That's our solution. This is our main script. This is our function to summarize the nonlinear equations, and we get the results that we're after. So let's come back over to our slides. And again, this summarizes what we've accomplished here with our two scripts and with our solution. At this point, we're going to terminate this particular screencast, and in the next screencast for Bootcamp 2 for MATLAB, we're going to move on and we're going to consider the solution of differential equations.